Welcome to True Projects. In this video, we are going to explain about the project entitled as a hybrid deep learning model for network intrusion detection system using sequence to sequence and convolutional LSTM subnets. So before getting into the video, let me give you the brief description about the project. This project focuses on building a hybrid deep learning based network intrusion detection system that combines sequence to sequence and convolutional LSTM subnetworks. The sequence to sequence model captures sequential patterns in network traffic, while convolutional LSTM learns both spatial and temporal features. By integrating these models, the system improves the accuracy and robustness of detecting normal and malicious network activities. Coming to the abstract explains that increasing reliance on computer networks has made network security more challenging, especially with the rise of complex cyber attacks. Traditional intrusion detection systems are limited because they depend on predefined signatures or simple machine learning methods that cannot effectively detect new or evolving threats. To address these issues, the project proposes a hybrid deep learning based intrusion detection system that combines sequence to sequence and convolutional LSTM models. The sequence to sequence component learns long term patterns in network traffic, while the convolutional LSTM components capture spatial and temporal features, resulting in higher detection accuracy, fewer false alarms, and better adaptability to modern network intrusion behaviors. Coming to the existing system, the existing network intrusion detection system mainly relies on rule based, signature based, or traditional machine learning techniques such as decision trees, SVM, KNN, and Navy bias. Although these methods perform well for detecting known attacks, they are ineffective against zero day or previously unseen threats because they depend on predefined signatures. Traditional machine learning models also require heavy feature engineering and fail to capture the sequential and temporal nature of network traffic. Even some current deep learning based systems use a single model architecture, which limits their ability to learn complex temporal and spatial patterns, resulting in reduced detection accuracy and higher false alarm rates. Coming to the proposed system, the proposed system presents a hybrid deep learning based intrusion detection approach that integrates sequence to sequence and convolutional LSTM subnetworks to address the shortcomings of existing IDS solutions. The sequence to sequence model focuses on learning spatial patterns in network traffic, which helps in identifying complex and time dependent attack behaviors. At the same time, the convolutional LSTM subnet captures both spatial and temporal features, enabling the detection of evolving the safety intrusions. By combining the strengths of both models, the system delivers more accurate and robust intrusion detection, reduces false alarms, improves zero day attacks detections, and adapts well to diverse and high speed network environments. Coming to the dataset, we have used three different datasets. Among them, the first one is network intrusion dataset, that is known as CICIDS 2017 dataset. The CICIDS 2017 dataset is widely used benchmark dataset developed by a Canadian Institute for Cybersecurity for network intrusion detection research. It consists of labeled network traffic data that includes both normal and malicious attacks, making it suitable for training and evaluating intrusion detection systems. The dataset covers a broad range of modern attack scenarios such as DOS, DDoS, brute force attack, and web based attack like SQL injection and XSS interfiltration and port scanning, reflecting real world network behavior. It also contains detailed network flow feature including IP addresses, port numbers, protocols, timestamp, and statistical traffic attributes, enabling researchers to build and assess effective machine learning and deep learning based intrusion detection models. Next, we have CICTO IoT dataset. The CICTO ITO dataset developed by a Canadian Institute for Cybersecurity is designed specifically for intrusion detection research on Internet of Things environment. It contains labeled network traffic collected from IoT devices and related infrastructure representing both normal device behavior and various malicious activities. The dataset includes a wide range of IoT specific attack scenarios such as DOS and DDoS attacks, reconnaissance attacks like pod scanning and pin sweep, spoofing attacks, brute force login attempts, and Mirai botnet based attacks. With structured network flow features similarly to other CIC dataset, CICTO IoT enables machine learning and deep learning models to effectively distinguish between benign IoT traffic and attack patterns, making it highly suitable for deploying and evaluating IoT force intrusion detection system. And third, we have UNSWNB15 dataset. The UNSWNB15 dataset was developed by a cyber range lab of the Australian Centre for Cybersecurity at UNSW Canberra to provide a more realistic and modern benchmark for network intrusion detection research. It combines genuine normal network traffic with synthetically generated attack traffic to better reflect real world network environments. The dataset contains over 2.5 million records with 49 features, including protocol information, flow statistics, content based attributes, and timing features. It covers a wide range of attack categories such as fuzzers, analyzers, backdoors, DOS, exploits, generic attacks, reconnaissance, shellcode, and worms, making it especially useful for training and evaluating machine learning and deep learning models, particularly for multi-class intrusion detection tasks. Coming to the novelty or extension or enhancement or improvement. In this extension, select K-best feature selection was applied to identify the most relevant features from the dataset, reducing dimensionality and improving model efficiency. A hybrid deep learning architecture combining LSTM and GRU was developed to better capture sequential patterns in network traffic. Additionally, a voting classifier was used to combine predictions from multiple models, which results in significantly improved performance, achieving 100% test accuracy on the CICIDS 2017 and CICTON IoT datasets. Next, to enhance the model transparency and trustworthiness, explainable AI techniques such as LIME were employed. LIME explains individual predictions by highlighting the most influential feature values contributing to the model's decision, helping users and researchers understand why a particular network flow is classified as normal or malicious. Furthermore, a Flask framework based web interface was developed to make the system user friendly and interactive. This UI allows users to provide input data and obtain real time intrusion predictions using the trained models, making the solution practical for deployment and easier for non technical users to interact with the intrusion detection system. Coming to the flow of the work, first we have import the packages. The workflow begins with importing all required Python libraries for data handling, pre-processing, visualization, machine learning, deep learning, and evaluation. These packages provide the necessary tools to manage datasets, build models, and analyze results. Next, exploring the dataset. Multiple intrusion detection datasets are explored to ensure data diversity and robustness. For the CICIDS 2017 dataset, all CSV files are combined into a single dataset. The CICTON IoT V2 dataset is loaded for a Parquet file, and for UNSWNB15 dataset, both training and testing CSV files are merged. This step helps in understanding feature structure, data distribution, and attack classes. Next, data pre-processing. Data pre-processing ensures data quality and consistency. Null values and duplicate records are removed to avoid bias and redundancy. Multi-class attack labels are converted into binary labels to simplify the classification task and improve detection reliability. Next, label encoding. Categorical features and labels are converted into numerical form using label encoding and one-hot encoding. The step is essential since machine learning and deep learning models require numerical inputs. Next, normalization. Feature values are scaled using minimax scaler to bring them into a uniform range. Normalization improves model convergence, speed, and ensures fair contribution of all features during training. Next, data visualization. Visualization techniques are applied to analyze label distributions and class imbalance. This helps in understanding the proportion of normal and attack traffic and guides model selection and evaluation strategy. Next, build the classification model. Multiple traditional machine learning and advanced deep learning models are implemented, including random forest, decision tree, navy bayes, XGBoost with random forest, CNN, convolutional LSTM, sequence to sequence, and LUNet. As a part of extinction, select K-best feature selection, outlier removal, a voting classifier, and a hybrid LSTM plus GRU models are also developed to enhance the performance. Next, training the model. Each classification model is trained using the pre-processed and normalized data. Training involves learning patterns that distinguish normal traffic from intrusion attempts. Next, model evaluation and comparison. Models are evaluated using performance metrics such as accuracy, precision, recall, and FN score. These metrics provide a comprehensive comparison of detecting capability and false alarm rates. Next, comparison graphs. Comparison graphs are generated to visualize, represent, and compare the performance of all models across different evaluation metrics, enabling easy identification of the best performing model. Next, save the best trained model. The best performing trained model is saved for future use and deployment, ensuring that it can be reused without retraining. Next, explainable AI visualizations. Explainability techniques such as LIME and SHAP are applied to interpret model predictions. These models highlight the most influential features contributing to classification decisions, improving transparency and trust in the system. Coming to the front end, a web-based Coming to the front end, a web-based front end is developed using the Flask framework, incorporating user registration and login functionalities supported by an SQLite database for secure access. The front end allows users to input network feature values required for intrusion prediction. User provided input data is pre processed using the same steps applied during model training to maintain consistency. The saved trained model is loaded and used to perform intrusion detection on the processed input data. The final prediction results is displayed through the front-end interface, providing users with a clear and interactive intrusion detection outcomes. The algorithms used in the project are random forest, decision tree, navy bayes, XGBoost plus random forest, CNN, convolutional LSTM, sequence to sequence, LUNet, and as an extension we have used select K-best feature selection, removing outliers, voting classifier, LSTM plus GRU. Coming to the requirements, we have both hardware requirements and software requirements. Hardware requirements consisting of operating systems Windows only, processor i5 and above, RAM 8 GB and above, hard disk 25 GB and above. Software requirements consist of application framework Anaconda, primary language Python, front-end framework Flask, backend is Jupyter Notebook, database is SQLite 3. Technologies which we use to build the front-end are HTML, CSS, JavaScript, and Bootstrap 4. To execute the project, first we need to open the code folder which contains the project source code files. This folder is a complete package of your project's code base containing everything needed to develop, test, and deploy your application or model. Static folder. This folder consists of files related to CSS, JavaScript, and Bootstrap. Templates folder. This folder contains all the HTML pages used in the project. It typically includes files like index.html, about.html, etc., which represents different pages of the website. App.py file. This .py file contains the information related to front-end logic. It could include code written in Python that handles server-side operations such as processing user requests, interacting with the database, and generating dynamic content to be rendered in the HTML templates. Models. These are the model files which contain the information regarding the algorithm, which will be loaded into the project code during the runtime. IPYNB files. These are the Jupyter Notebook files which contains a combination of code, graphs, and outputs all in one place. It allows users to write and execute the code in individual cells, making it a popular choice for data science. Signup.db file. This file is a database file used to store the user information. Coming to the execution of the project, first, you need to copy the path of the code folder from the address bar of the file explorer. Then, open Anaconda prompt. Use the command cd followed by a space and then paste the copied path. This command is used to change the current directory to the code folder's path. Now, compile the app.py file using the command python space app.py. This command will execute the Python script and perform a runtime check for any syntax errors or logical issues. After running the app.py file, the Flask framework will host the application locally at the default address with the port number of 5000. Copy the local link provided by the framework and paste it into any web browser. I prefer Chrome. The home page of the project should now be displayed in the browser. This is a front-end built using Flask framework. In this page, we have home button and user button. Firstly, click on user login button so that the create account form will be opened where you need to enter the details and create an account for user authentication like full name, username, email ID, mobile number, and a strong password. Again, reconfirm your password. Then click on sign up so that all the given details are stored in signup.db and the login HTML will be open where you need to access the application with the help of username and password so that the prediction page has been displayed. In this page, we have home button, prediction button, graphs and analysis button. In this page, we have home button, prediction button, graph and analysis button, notebooks button and logout button. Firstly, click on prediction button. As we are using the three different data sets, we will only find the output for two different data sets because the third data set which we have used has not reached the proper accuracy. So let us go with two different data sets. First, we have CIC-TON data set. When you click on that button, the CIC-TON data network intrusion detection system form will be open where you need to enter the inputs. Now let us check one by one. The protocol information value is of 6. Forward packet length maximum value will be 1448. Forward packet length mean value will be 367.6. Forward packet length standard value will be 627.12744. Packet length maximum value will be 1448. Average packet size value will be 545.4545. Average forward segment size value will be 367.6. Subflow forward packet value will be 0. Subflow forward bytes value will be 167. Initial forward win bytes value will be 29200. And now click on predict so that the input values are pre-processed and the output will be displayed as benign. For the given input values, it is benign. Confidence score is of 99.98%. We also have like flow analyzed, analysis type, features used, response time. We have what does this mean, suggested checks, recommended actions about this prediction. Now click on new prediction so that the CIC-TON form will be opened again where you need to enter the network flow features to analyze the traffic patterns. So the protocol value will be 6. Forward packet length strategy will be 417. Forward packet length maximum value will be 417. Forward packet length mean value will be 83.4. Forward packet length standard value will be 186.48807. Packet length maximum value will be 883. Average packet size value will be 1. 88.77777. Average forward segment size will be 83.4. Subflow forward packets value will be 0. Subflow forward bytes value will be 46. And initial forward win bytes value will be 29200. Now click on predict so that the input values are pre-processed and the output is displayed as an attack. The confidence level is 100%, like it is a potential attack detected. We also have flow analyzed, analysis type, features used and response time, and what does it mean, and suggested checks and the important recommended actions has been displayed. And we also have the other information like about this prediction. Now click on the other data set, that is CICIDS. When you click on that, the CICIDS data network intrusion detection form will be open, where you need to enter the network flow features to analyze the traffic patterns. In this, the backward packet length maximum value will be 0. Backward packet length mean value will be 0. Length standard value will be 0. Forward IAT standard value will be 0. Maximum packet length will be of 6. Packet length mean value will be of 6. Packet length standard value will be of 0. Packet length variance value will be 0. Average packet size value will be of 9. Average backward segment size will be of 0. Then click on predict so that the input values are pre-processed and the output will be displayed as benign. The confidence score is of 100%, which means it is a normal network traffic detected. We also have the flow analyzed, analysis type, features used, and response time. And what does this mean? And also with suggested checks. Along with that, we have the recommended actions and about this prediction. Again, click on the new prediction so that the CICIDS data form will be open, where you need to enter the values. The backward packet length maximum value will be of 0. Backward packet length mean value will be 0. Backward packet length standard value will be of 0. Forward IAT standard value will be 0. Maximum packet length value will be of 8. Packet length mean value will be 4.8. Packet length standard value will be of 4.3817805. Packet length variance value will be 19.2. Average packet size value will be of 6. And average backward segment size will be of 0. Now click on predict so that the input values are pre-processed and the output will be displayed as an attack has been detected. It is the confidence score is of 99.99%, which means the potential attack has been detected. We also have the forward analyzed, analysis type, features used and response time. What does this mean? And also suggested checks along with the recommended actions and about this prediction. Now click on graph analysis. So this also let us check for one by one data set. First, for CICTON data set, when you click on that, the graphical representations for CICTON will be open. Let us check one by one. First, we have label distribution graph. The graph shows the distribution of binary class labels in the dataset, where label 0 represents normal traffic and label 1 represents attack traffic. Both classes have nearly equal counts, indicating a well-balanced dataset. This balance helps improve model training by reducing bias towards any single class. Next, we have confusion matrix graph. The confusion matrix shows that the model correctly classifies most normal and attacks samples, indicating strong detection performance. A small number of normal insanes are misclassified as attacks, and some attacks are missed. Overall, the high true positives and true negative values reflect the model's high accuracy and reliability. Next, we have accuracy graph. The graph compares the accuracy of different machine learning and deep learning models used for intrusion detection. Hybrid and deep learning models such as voting classifier, convolutional LSTM, sequence to sequence, and LUNet achieves the highest accuracies, outperforming traditional models like Navy Bayes. This highlights the effectiveness of advanced and ensemble approaches in detecting network intrusions. Next, we have precision graph. The graph illustrates the precision scores of different models, showing how accurately each model identifies actual attack incidents. Advanced deep learning and ensemble models such as voting classifier, LUNet, convolutional LSTM, and CNN achieves higher precision, indicating fewer false positives. Traditional models like Navy Bayes exhibits lower precision, reflecting weaker intrusion discrimination. Next, we have recall graph. The bar chart shows the recall performance of different machine learning models. Deep learning models like CNN, convolutional LSTM, sequence to sequence, and LUNet achieves higher recall, with the voting classifier performing the best, while traditional models like Navy Bayes have lower recall. Overall, ensemble and network models outperform simpler algorithms. Next, we have FN score graph. The bar chart compares the FN scores of different machine learning models. Neural networks models like CNN, convolutional LSTM, sequence to sequence, and LUNet generally performs better, while Navy Bayes has the lowest FN score, indicating weaker predictive performance. Overall, voting classifier achieves the highest score, suggesting ensemble methods can be very effective. Next, we have explainable AI SHAP graph. This is a SHAP summary plot showing how different feature impacts a model output. Each dot represents a data point. Position on the x-axis shows the feature effect on prediction, and color indicates feature values. Features at top, like initial forward wind bytes, have the most influence on the model. Next, let us check with CI/CD dataset. When you click on that, the data visualizations of this dataset will be open. Let us check one by one. First, we have label distribution graph. This bar chart shows the distribution of two labels, benign and attack. Most of the data points are benign, with nearly 1.8 million entries, while attack insanes are much fewer, around 0.43 millions, indicating a highly imbalanced data. Next, we have confusion matrix graph. This is a confusion matrix showing how well a binary classifier performed. Most samples were correctly classified with very few errors. Overall, the model performs extremely well, especially at identifying the positive classes. Next, we have accuracy graph. This bar chart compares the accuracy of different machine learning models. Deep learning and ensemble models achieve nearly perfect accuracy, while Navy Bayes performs slightly worse. Overall, more complex models clearly outperform simpler ones. Next, we have precision graph. The bar chart shows the precision score of different machine learning models. Most models, especially deep learning and ensemble methods, achieve very high precision, meaning fewer false positives. Navy Bayes has noticeably lower precision compared to others. Next, we have recall graph. The graph compares recall across different machine learning models. Deep learning models and voting classifier achieve nearly perfect recall, while traditional models, especially Navy Bayes, perform noticeably worse. Next, we have F1 score graph. The graph shows the F1 score comparison across different machine learning models. Deep learning models and the voting classifier achieves near perfect F1 scores, indicating a strong balance between precision and recall, while Navy Bayes performs slightly lower than others. Next, we have explainable AI SHAP graph. This SHAP summary plot shows how different packet related features influence the model's prediction. Features like packet length mean and maximum packet length have the strongest impact, where higher values generally push the prediction upwards with lower values reducing it. And now let us check the graphs for the third data set. In this first, we have label distribution graph. The bar chart shows the distribution of labels in the data set. Label 0 has the higher count than label 1, indicating a mild class imbalance. This means the model will see more examples of class 0 during training than class 1. Next, we have confusion matrix graph. This confusion matrix shows how well the model predictions match the true labels. Most predictions are correct with some false positives and fewer false negatives. Overall, the model performs well, especially in correctly identifying class 1. Next, we have accuracy graph. The bar chart compares the accuracy of different machine learning models. The voting classifier and random forest achieves the highest accuracy with LSTM plus GRU performs the lowest. Overall, ensemble and deep learning models generally outperform simpler models. Next, we have precision graph. The bar chart compares precision across different machine learning models. The voting classifier and deep learning models shows the highest precision while navy bias and LSTM plus GRU perform comparatively low. Next, we have a recall graph. The bar chart shows the recall performance for different ML models. The voting classifier and deep learning models achieve the highest recall, while navy bias and LSTM plus GRU have relatively lower recall values. Next, we have F1 score graph. The bar chart compares the F1 score of different ML models, balancing precision and recall. The voting classifier and deep learning models achieve the best overall performance, while navy bias and LSTM plus GRU shows lower F1 scores. And next we have explainable AI SHAP graph. This is a SHAP summary plot showing which features most influence the model prediction. Features at the top have the biggest impact and points to the right increases the prediction while those to the left decreases it. Color shows feature values, red equal to high values, blue equal to low values, revealing how high and low values push the model output. And next click on logout. So finally, this project successfully demonstrates a hybrid deep learning based network intrusion detection system that integrates sequence to sequence and convolutional LSTM subnetworks to effectively detect complex and evolving cyber attacks. By capturing both long-term sequential patterns and spatiothermal features in network traffic, the proposed model achieves the highest detection accuracy with reduced false alarms. The result shows improved performance over traditional and single model approaches, making the system reliable and suitable for modern, high speed network environments. So, this is all about your project. Thank you.
Thank you for watching video. For more projects, please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.